I talked about glass transition temperature before, and I'll come back to it. It's a temperature which the material, the thermoset material goes through a phase change. So it goes from being a brittle, glassy material to being a rubbery kind of material. So on the chart here, I've just shown a material, standard FR4. FR4 is just a classification for basic base materials. So if you look at the bottom there, there's a thing that says (1). It should say alpha 1. We did fix that yesterday, but it seems to have unfixed itself again. So this little line at the bottom between 25 and 135, this is the coefficient of thermal expansion up to the TG. So 135 is the softening point of this resin. And you see there's a fairly low, shallow line. And I'll put a number on that. It's probably 40 or 50 parts per million per degree centigrade. Once you hit the TG, you suddenly go through a phase transition. And all of a sudden, you go to this (2) rate, which is around 300 ppm per degree C. So there's a step change in the expansion coefficient. And then if you get to 200 degrees, let's say just as a random number, you find this line. So if you intersect the 25 degrees line at the bottom here, so go from here to where this top line is, I'm not tall enough, across there, that's how much you expand over that temperature excursion. If you go for a higher TG material, so this now has got a TG of 175 instead. Basically, all we've got is a bit longer at the lower rate. So you see it's still the same rate, more or less, but we go on 175 at this, say, 40, 50 ppm per degree C rate. And then between 175 and 200, then we have the high rate kicking in. So we intersect at a much lower point. And actually, that's where we intersect now. So if we look at those two materials, that's the difference. So overall, just because we've got longer at the lower expansion rate, we end up with a lower expansion rate of the material. And that really is a crucial difference. If we think about the TG in terms of what it means to the chemistry, this is just an example of how carbon bonds look. And we're giving it more degrees of freedom, and we're allowing it to rotate a bit more, and we're breaking some of these weak bonds. And actually, when you get above the TG, you get into this situation where the molecule can move around all over the place. Associated with that, the phase change, there is also an energy change. This is an endothermic reaction. So when you go through the phase change, this takes energy in, and that's how we measure it generally. We use a calorimeter to measure this energy change. I brought some white powder, which is always a bit dangerous going through airports, but I did bring it with me. This is phase change powder. If you be careful not to throw it everywhere, but if you take this material, you can actually feel the energy change, the phase change. This contains microbeads. The microbeads contain wax, which melts around 23 degrees centigrade. So when you put your fingers in there, you melt the wax, and you'll then feel it feels cold. There's nothing in there, I'll prove it's completely innocuous. But if you try that, you'll feel your fingers go cold. Just leave it in for a second. And just hold them in there and say, try not to pour it everywhere. But that's a physical example of how the phase change works. That material is used in thermos flasks. It's formed into composites like this. So we use that material into with a matrix material, a resin around it, if you like, to form a material that just gives you that little extra time to transition through a temperature range, whatever the temperature range is. So when you hit 23 degrees centigrade in here, you reach a plateau and you wait there, and then eventually enough energy is submitted to the material that it actually then will melt. So that's what the phase change actually feels like. Hopefully it makes sense to everybody. So there's no mousetraps in there, believe me. I've still got to get the white powder out through the airport, but hopefully I'll manage that.